Hi, my name is Jae-Pyong Kim from the Artificial Intelligence and Mobility Lab of Korea University. Today I'm here to present to you about visual simulation software demonstration for quantum multi-drone reinforcement learning. The overall contents of my presentation will be as follows. I will first talk to you about the system overview, and then the Q policy, the proposed visual simulation software, the QMARL simulation results, and then I'll conclude my presentation. Firstly, for the system overview, our motivation for the work is shown here. Quantum computing has received a lot of attention lately thanks to its computing potential. And we propose a hybrid quantum classical multi-agent reinforcement model. However, there has been no visual simulation framework for a QMARL model, which is why we also designed one for this framework. By using quantum computing, we were able to greatly improve the performance of the model compared to previous classical applications, corroborated by extensive simulation results. Now I will explain to you about the Q policy network. The figure here shows the structure of the Q policy network. In the computation process, data reuploading is used by a sequence of encoders and Q layers as shown here. Encoders are composed of basic quantum rotation gates, which are attributed with classical state data information. The Q layer is composed of the control U3 gates, which causes entanglement between qubits. Finally, we have the measurement layer. In the previous step, output quantum state is produced by data reuploading, but this must be measured first in the measurement layer by applying a projection matrix onto the reference z-axis. This can be used to calculate the optimizable loss function. Next, I'll elaborate to you about the entire structure of our framework and showcase an actual demonstration. This is the drone environment layer, where the multiple drones try to train the policies. And then next, for the MARL layer, you can see the nth agent's policy is comprised of neural networks. And then we have the quantum layer, and then we have the trainer layer, where we will update the weight parameters of the neural networks and decrease the loss function. Finally, in the visualization layer, the training process of the agents are analyzed by using a visualization tool. Now we will show you a video of the model demonstration. So you can see here that we are executing our code by using Visual Studio. So once the training is started, we need a way to visualize the training being done in real time. And this is where TensorBoard comes in. So by using the code that we are writing here right now, we can call TensorBoard to show the results of our training. And as you can see here, the results of our training is shown by the value of the reward, the quality of service, and the drone trajectory as shown here. This changes with time, as you can see. And then again, there's the reward value, the quality of service value, and the support rate value. We can change the outlook of the graph by changing the smoothing coefficients. And when we set it to 0.6, we can see the values of the reward changing over time, as well as the quality and the support rate. So now that, and you can see the drone trajectory again changing over the time steps as it is optimized. And then now the training is finished, we can obtain the result by using a CSV file. So we can see here that we just downloaded a CSV file for the total reward. And then this CSV file can be used to extend the results from TensorBoard to MATLAB. As you can see here, this is done by MATLAB, and you can see that our quantum hybrid model is performing better than the classical model, which proves our point. And then in conclusion, we propose the visual simulation software framework for QMARL, and this can validate that our proposed QMARL based algorithm has more efficient training than classical MARL. And with that, I conclude my presentation, and thank you for listening.